Hey, 12th graders. Uh, we are now approaching the end of this unit and kind of wrapping up this whole idea of what a integral is, kind of with like a nice little bow on top. So we've talked about how to find the integral. We've talked about the integral being the backwards movement of derivatives. We've talked about how we can use it to further understand those tiered relationships of equations, of like moving from your displacement to your velocity to your acceleration and all the way back up. But not just with that specific instance, when we're talking about any type of rate of change, whether we're talking about an increase in volume or a flow rate or any of those things, how to be able to move back and forth between those tiers of equations. That integrals are a fantastic tool to kind of build off of that understanding that we already had with derivatives. We then said, hey, well, isn't it also kind of cool that these values that we're trying to find when we're going back to what we call our original function, that we actually technically don't even need to find that equation in order to find those values, that those values can be found by just evaluating the area underneath the curve. And that's kind of how those relationships go hand in hand. So we spent last lesson just kind of talking about how we use definite integrals to find the area between 2 points on a curve, underneath the curve, between the curve and the x-axis, or like between two curves, how to deal with composite figures. And now we're talking about, hey, what if we don't have an equation? What if we are out in the real world and we've gathered data and we have a rate in which something, I'm assuming like water, has flowed into some sort of basin. And we gathered data at certain hours, okay, at hour 0, 2, 4, 6, 8, and we've got this scatter plot. Now we could go through the whole process of trying to create a model that best represents this scatter plot, put it all together, and then find the integral underneath the curve. But we don't have to do that in order to find a really good approximation of the area underneath the curve. And when you're not looking for the most exact as possible, having some sort of an approximate is a good way to kind of just lean into to this idea when you're a scientist and say like, okay, well, about what? Like, right, I did this and this ends up telling me about something, and an approximate of that situation. So we use this for when we don't have an equation, like a scatter diagram. We can also use this if the equation is too difficult. EQ for equation. So if the equation is too difficult to integrate, that it's a little bit more complicated of a process, then we can use this as a way to kind of break it down. And again, I want to put even further emphasis on this is an approximation of the area underneath the curve. We're going to try and get as close as possible as we can, but it's definitely not the exact area underneath the curve. What we're doing, what we're about to learn, is called the trapezoidal rule. The trapezoidal rule. So we've got this scatter diagram. And if we wanted to create an equation that kind of best represents this scatter diagram, our equation, our curve, might look something like this. And we don't have the equation, but we do want to talk about the area underneath that curve. And so what we do is that we split this curve into a segment amount of, let's say at first, rectangles, right? So we kind of divide up this space into equal segments that say, okay, I'm going to chunk up this total area into smaller pieces so it's easier for me to understand the whole by understanding the pieces, your composite figures, right? So we've got these rectangle ideas. And what we want to do is we want to find the areas of each of those sections. And so what we do is we kind of close off the polygon because we like nice straight lines when we're dealing with geometry and finding areas of polygons. We like to have these nice straight lines, and the curves kind of throw us a little bit. So instead of having a curve here, what we do is we connect that dot and that dot. And the polygon that we end up getting is what we call a trapezoid. Trapezoids have two parallel sides. The other sides, so for instance, the heights here are your two parallel sides. And then the other heights or the other lengths. It doesn't matter if they're parallel. It doesn't matter if they're skewed. It doesn't matter if they're going in the same direction, right? No matter what, it's a trapezoid. So just a really quick refresher, area of a trapezoid. Your trapezoids have two parallel bases. So let's say we've got a trapezoid that looks like this. As long as those guys are parallel, that is a trapezoid, right? You can also have a trapezoid that looks like this. These guys are parallel. And even if that's a right angle, and even though it looks slightly different, it's just the defining factor here is that those opposite sides are parallel. So those opposite parallel sides we call bases. We call it base 1 and base 2, no matter what. Even if your trapezoids are rotated, right, and on the side, it's still your parallel sides that are called the bases, right? So we can always shift or move or rotate a shape around, and that idea of a base kind of shifts with it. So a base doesn't necessarily mean the side that it's lying on. It just means a specific relationship within the diagram. And for this particular diagram, it means those parallel sides. Another dimension that we care about with trapezoids is the height. So the height would be the distance between those two bases. It can be up and down like it is in here. Remember that height is always that perpendicular direction. It can also be here. You can see that we've already got a perpendicular direction, and it just happens to be that side length that represents the height of that trapezoid. In this instance, if these guys are perpendicular, the height is the distance between those two bases, even though it looks like it would be intuitively a base because it's laying on that side. It's not. It is the height because it's that distance between our idea of two bases, because that idea of height still travels with the diagram when we rotate it. So the area of a trapezoid is 1/2 times your height times your base 1 plus your base 2. Now that is in your formula packet, so you definitely don't have to have it memorized, but I do want you to know that this is the relationship of your dimensions, and that is important to keep in mind. So we use that idea of, hey, we know how to find the area of a trapezoid. Notice that this trapezoid right here looks a whole lot like these trapezoids over here. So we've got this first trapezoid, and we can go on and continue creating these trapezoids until we've represented the whole area. Now we can see that our trapezoids, this is where we lean in again to the idea that this is an approximate. We can see that this area is not quite there, right? We've missed some of this area above the curve, and notice that we've counted too much area over here where the curve goes below our trapezoid. And that's the give and take of using the trapezoid rule, of the idea of the approximation of all of this, is that you might be overcompensating in some areas and undercompensating in others, but the idea is that you're getting really close to what it actually is. So if we wanted to find the total area, we take all of these areas and we add them together. So we have 4 separate parts of this area. And so our total area will be equal to just adding all of those areas up. Your height is going to be the distance along that x-axis of each trapezoid. Notice that they are equally spaced. That is going to be key here for your trapezoid rules, that you have equally spaced height on x-axis. So if you have a distance of 2 for that height, they need to continue to be a distance of 2. And then your bases, how do I represent this? It doesn't matter which one's base 1 and which one's base 2. Notice it kind of like shifts around here. It wouldn't really matter which one's base 1 and base 2. So I'm calling this one base 1, but you could call it base 2. And then this length right here is your base 2, right? So what you're doing is you're adding these two heights together for each of them. So A1, we're adding the two heights on either side because these are our two bases. Recognize that our two heights are our y values of the points, right? So this height right here is 12. And then our second height is 17 halfway through. You can see that from the table of values up above. You can also gather that from the graph. So base 1 plus base 2 times height, which is 2, and then times a half. All right, and that is how you find the area of one of those trapezoids. 1/2 times 2 is just 1, so then it just becomes 12 plus 17, which is 29. And then we continue. Okay, well, 1/2, and since we know that the height is always going to stay the same, it's always going to be that distance of 2 along, then we just know that's still 1/2 times 2. And then we take each of those y values and add them up. We've already established that this is a height of 17. And then our next height is over here, and that's 18. 1/2 times 2 is just 1, so 17 plus 18 is 35. Move on to the next one. It's still going to be 1/2 times 2 because that's same height. And then we know that our last y value is 18, and so now we're just adding in 16, our new height over here, 16, which you can also grab from your table above. And then A4 is going to be 1/2 times 2 again. And then we've got 16 plus, we can grab it from our table up above, or we can see right here that it looks to be about 15. Adding those up, we get 31. So when we find all the areas of each of these trapezoids, all we have to do is then add all of those areas together. Go ahead and add those all up for me, just adding up area 1, 2, and 3, and 4. Adding those up, you should get 129. Exactly. Now realize that I did put approximate symbols here, and I did that on purpose. It's a nice, solid reminder to be like, this is the approximate area under the curve. I've approximated it by making a composite figure of trapezoids to represent this area. And so I know that 129 is not going to be the exact area, but it's a nice, quick way for me as a scientist to be like, oh, okay, well, the amount of volume of water that went into the tub over the course of 8 hours was 129,000 meters cubed, right? So if we're talking about finding the integral, we're multiplying our units of the y-axis to our units of the x-axis, the hour would cancel out, and we're left with thousands of meters cubed. So we would know, okay, we got to the end of this experiment, we had about 129,000 meters cubed of water, of whatever. Really quickly, this tiny graph to the side, if we continued with this curve, like if we redid this curve, and we wanted to be as close as possible to get a little bit more exact, notice that if we kept with this, right, we have a certain type of approximate. The smaller your spacing is, the more accurate your approximation is in regards to that area underneath the curve. Noticing that that curve is going to start to look a lot closer to our trapezoids. That like that part of the trapezoid seems to almost be exactly with the curve a lot more than these trapezoids did. So smaller spacing